In this particular presentation, um, I'm going to talk about some interesting aspects of interval estimation and how that will help us with the hypothesis testing. As we have seen, the logic of confidence interval is based on the sampling distributions. If it's a quantitative variable, it is the sampling distribution of x bars. If it is our categorical variable, it is a sampling distribution of p hats. As you know, both these distributions we assume are normal. If and when they are normal, given the larger in size of the sample, we can use this particular formula for quantitative variable and this particular formula for a categorical variable. Now, when you have a sampling distribution, we know that you can calculate the z. The z for x bar would be x bar minus mu by sigma x bar, which is the standard deviation of sampling distribution. Similarly, the z for p hats would be p hat minus p by sigma p hat, but sigma p hat is the sampling distribution of sample p hats. So I can introduce why we need t. In real life situations, we actually do not know the sigma in the population. In that sense, in that case, we'll calculate the sigma x bar, not by using the sigma of the known population, but using the sample statistic. And then won't need z, but we'll calculate a different test called t statistics. And that's what we'll talk about in this particular video. Okay, so for a population of for a quantitative variable with mu, which we are interested in knowing. And if we already know the sigma for it, and if you have a sample x bar with the sample size of n, we said that we can imagine that this sample is just one of the thousands of samples from a theoretical sampling distribution of all x bars, such that the center of this is represented as sigma x bar, which would be equal to the population, the mu, and its standard deviation of this would be equal to sigma of the population over square root of n, which is where n is the sample size. We also said that this is a formula to calculate the z in that instance. And this is a formula we have been using to calculate the confidence interval, right? Now, what happens when the sigma is not known? Can we still use the z? In other words, can we still assume that the distribution is normal? The answer is no. If we use S, which is a sample statistics, instead of sigma, which is a population parameter, then the assumptions are violated. In other words, we do not know, we cannot be certain that this sampling distribution of sample x bars is now normal. So the central limit theorem would not be applicable, and the normality function or normality assumption is not met. And then we cannot use the z multiplier that we have used here. In other words, we don't know if 95% of observations will fall here because we don't know that this is normal. In that case, we'll use a different kind of multiplier, and that multiplier is called t. A t multiplier comes from a t distribution, just like a z multiplier comes from a normal distribution. A normal distribution is a distribution that is symmetric unimodal, right, with a high peak and very low tails. A t distribution is slightly different. So when you use sigma, then the sigma x bar, which is calculated by sigma or square root of n, is called standard deviation of sample means. Standard deviation of sample means in a sampling distribution, that's what it is. But the moment you change the sigma to s, then this is no more called the standard deviation of x bars. It's actually called standard error. It's called standard error. So how are the t and z distributions different? Well, if you look at it, the formula for calculating z is x bar, which is your sample value, minus the known population value, right? And or the population value they think you have information about, divided by sigma over square root of n. This is called the standard deviation of x bars. The formula is similar for the t-test. This is a z, this is a t, but there are two sources of variation here. As you can see, the z value here can change depending on the sample. If you take one sample, if you take the sample once, it will change. If you take it another time, it will change. Third time, it will change. Fourth time, it will change again. So the source of variation for calculating z is only one, because the sigma doesn't change for a given sample size. In the population sigma is always the same. But when it comes to the t, you can see there are two sources of variation. The t value can change depending on the value of the sample, and also the standard deviation of the sample, which is not constant as it is, as the sigma is. But the interesting thing is that the t distributions and Z distributions are pretty much similar. They are both bell-shaped. Remember, I talked about the two common forms of bell distributions. One is bell normal. The other one is T random and normal random and T random. Well, normal random is specific to the Z score, and T random is specific to the T distribution. So the difference between a T distribution and a Z distribution is that a Z distribution has a high peak and a flat, you can see that in the black one, flat tails. So that specifically 95% of observations will fall between two standard deviations. But a T distribution, on the other hand, is has a lower peak but has elevated tails. This makes the distribution slightly different, and it's called T distribution. And as you can see, with the increase in the sample size, the T distribution actually approaches closer to the Z distribution. So what does it mean? Well, if you know the sample population sigma, then you can calculate the Z by using this formula, and you can use the Z table. But if you're not using sigma because you don't know and you're using the sample statistic, and if the sample size is smaller, in that case, you'll calculate the t and use a t table. But with a larger sample size, usually greater than or equal to 30, then you can still use the z-test, because with the increase in sample size, the distribution of t approaches normality. Okay, what's the bottom line? Well, if you have one quantitative variable, you can either use z-test or t-test, z-test or c-test. For the confidence intervals, you can either use the z-score or t-score, depending on whether or not you know the population sigma. If you know the population sigma, you're going to use z confidence multiplier, and you can calculate the z-test, z-score. If you don't know the sigma, then you're going to use ES instead, and you're going to use this formula with the T multiplier for the confidence. And you're going to use a formula for T utilizing S as opposed to sigma. Then that basically z-test and t-test are two different kinds of test statistics that you'll calculate for one quantitative variable situation. If sigma is known, you calculate z-test. If sigma is not known, you call t-test. In fact, this particular t-test is called one sample t-test.